want to just look at the summary of the. So we'll go through the concrete PowerPoint slides. That's the bulk of the information here. But there's a whole host of other little bits and pieces that you can have a look through in your own time. Plenty of resources there. And one of the we've got all sorts of concrete which is used in the commercial context. For the research task, I get you to look at pre-stressed concrete floor panels. So, well, there are a couple of different manufacturers of them. Delta Corporation produce a panel which is lightweight, pre-stressed panel that can span long distances, and they will be running the services and things through there. And that's the link to their website for having a look at that. So we'll be looking at concrete in a broader context, looking at a whole host of things in commercial application, but this one's a bit more specific to the research task. Jump up here so that the thing follows me. Or if can't put it, no, I can't do that. So reinforced concrete, ideal building material for commercial buildings, strong and durable, very high resistance to fire. Definitely stands the test of time. So plenty of Roman ruins about. A lot of concrete gets stronger with age. I guess one of the Achilles heel of that is steel. If the steel within the concrete starts to rust, well, then it can undermine that. But it can be cast into almost any shape as well, which is a fantastic thing. So the design of the freedom to cast concrete into almost any shape is limited by the cost of the formwork. So you can either cast elements like this on site, which is pretty crazy formwork, or you'll cast those off-site, reusing forms, and then take them to site. So the reinforced concrete may be used for the primary structures such as load-bearing walls, footings, floor slabs, floor beams, or columns. So if we look around, in this building here, we've got a lot of floor slabs, and these are post-tensioned floor slabs. Load-bearing walls, or you have concrete load-bearing. Well, we've got concrete lift shaft just outside the door there, which is taking weight from our floor plus some roof loads. And we've got plenty of columns about the place and beams integrated in with the floors. Commonly used typically for more industrial applications, concrete walls, so load-bearing concrete precast panels, which are generally cast off-site. So it avoids disruptions due to weather, enables reuse of formwork, enables tight controls of quality over those slabs, and some sites just don't have the space for casting as well. They can be cast on site, and that's typically done when you've cast the floor slab already and you've got this dead level surface to be working on. Then you cast one panel after another. So you cast a panel, when that panel's firm enough, then you create formwork on top of that, cast another panel on top of that. The difference in terminology between those two is that if it's cast somewhere else, it's called precast. If it's cast on site, it's called tilt up. because it's it's not precast anywhere else. So all you have to do is tilt it up. Very important that there's forethought for how those panels are going to be strutted on site. So strutting will have to happen. You also have to think about location of a crane and how the crane can get in there and tilt the panels up or lift them into place. You may have to think about road closures and book road closures in beforehand. And also you have to think about your sequence of tilting slabs up as well. So the first slab you want to be tilted up will be the last slab that you cast on site. So that's going to be on the top of the pile. Concrete's also used extensively for footings. Is that going to follow me? Yeah. Sort of. Yeah. Actually. There we go. So, concrete used extensively for footings. Yeah. Within Adelaide, we don't use a lot of strip footings. Simply because of the reactive soil, but strip footings can be fantastic for retaining walls and independent structures. One thing you will see around quite a lot are construction systems where you've got concrete beams and concrete columns holding up a slab. So if we were to dig down underneath a residential slab, that's pretty much what we'd see already anyhow. A whole series of internal beams and then slabs, or the slab top spanning between those. So that's a very common structure, be it suspended or on ground. Concrete's great at resisting compressive forces, but not good with tension, as we know. So without reinforcement, it will crack. Although things you can do to help with that tensile force is vibrating concrete sufficiently, because as soon as you get all the air bubbles out, you eliminate points of weakness there. But the main reason for placing steel reinforcing in concrete is to increase tensile strength of concrete. So an important part of the engineering is deciding on the placement of that steel. So if we were to have a few points of support, so point of support, and our slab going across the top there like that, then where we're spanning between elements, we want our reinforcing on the bottom of our slab primarily, but where we're going over top of something to a cantilever, then we'll want our reinforcing primarily on the top, because that's the bit which is going to be most in tension, as this thing wants to bend downwards, and this is the area that's going to be in tension as that wants to bow downwards like that. So like all building reinforced concrete structures need to resist dead loads, live loads and wind loads. Can anybody tell me what is a dead load, what's a live load?
Yeah.
Yeah?
A dead load is basically building self-weight. Live loads are the things, people, whatever that comes and goes, whether it be longer term or so you've almost got like semi-dead loads. And wind loads are horizontal forces that hit against the walls.
Yeah, exactly. And wind loads, we look at those wind loads in two directions typically, because we assume that, we assume wind can come from any direction, basically. Sometimes within inner city developments and things like that, the wind loads need to be forecast a little bit more accurately than that, because you're dealing with tall structures and complexity of wind paths, and you get concentration of forces from the presence of other buildings as well. Yeah, so things like in this building here, well, when it used to be a car factory, there's that massive gantry crane that runs through this central corridor here. That's also a live load that would have had to have been designed for as well. So it's all of those things. So sometimes our lives,
it's never going anywhere.
Now it's a dead load. Yeah.
Yeah, when it was a active gantry crane.
Oh, when it was active.
When it was active, it
Yes.
would have been a live load because it's a load that's constantly shifting back and forth across the entire factory.
Yeah.
Plus, sometimes it would also have the weight of an entire car on it.
Oh, absolutely. But I mean, like, the thing about it is that the self-weight of the gantry was never going to be it was never going to be a live load. It's actually the movement of the things across it, because like we know that it's not been taken out. That's why we know it.
Yes. Yeah.
But
So
we only
yeah.
know in retrospect, you know.
Yeah. So now it is a dead load.
Mm.
Yeah, certainly. But when this building was designed, you'll notice that those steel columns that hold up that gantry crane are really strong and very well reinforced. Yeah, to take that. So those the forces moving backwards and forth with with gantry crane with cars on it and things like that. Loads are imposed because of height and or shape, but also possible seismic loads. Not a real problem here in South Australia. I think it's sort of towards Paratilna or so. That's the centre of the seismic activity in South Australia, but it's still pretty innocuous. Torsion is a twisting of the structure around its main axis, and this results from when the lateral loads do not pass through the centroid rigidity and through the vertical load-bearing elements. Basically, when you've got a force happening on one side of a building that's not happening on the other side as well. So, yeah, tall building in the city that gets concentration of wings heading around one side of the building. Obviously, as drafters, probably, even as designers, we're not stepping into that and analysing that at all. That gets gets passed on to engineers, and same with designing structures to resist earthquake forces as well. So we can AS 1170 Part 3 deals with earthquakes, and basically it's a risk-based Australian standard that says, okay, there's this particular risk of seismic activity, and then you have to design according to that risk. But it's not a serious concern, particularly for us in South Australia, and not really for small-scale buildings, particularly residential buildings. But if we were doing, nuclear waste storage or something like that, well then, obviously, or particularly tall buildings. So precast concrete that is cast and cured in a location other than its final position or structure. So that's some pictures from a Bianco precast down at Cavan, I think they are, on Cavan Road. Casting all sorts of bits and pieces, stormwater pits, and many bits and pieces. So it's not just flat panels that go out. And then in situ concrete. So concrete is placed in its final position when it's in its plastic state. Does enable. Well, there are pros and cons. So your precast can be incredibly expensive, and you have to get it to site. Some sites it can be easier to get a concrete truck and a concrete pump than it can be to get a semi-trailer with large panels, because pumps, 100 diameter or 150 diameter pipe, you can run that through some things. But formwork can be incredibly expensive because it's very labour intensive. It needs to be constructed on the site and then pulled down again. Formwork has a limited lifespan, particularly if it's high quality finishes that are required. So once you start putting cutting up form ply, putting screws and things like that into it, and then taking that apart, it's not going to look quite the same again. And so that's put together by formwork carpenters as well, which is actually quite. I think it's not probably not as respected as it should be, because I think formwork carpenters need to have real attention to detail, and they're dealing with tricky shapes and tricky angles pretty much all the time as well. So I think it's one of the trickier carpentry jobs. Right, so pre-stressed concrete. So it's tensile stress resistance is incorporated in concrete element by way of steel tendons that are subjected to pre-tension. So this, you're not going to, well, I don't know of any pre-tensioning that happens on site. You certainly have post-tensioning that happens on site. I haven't seen any pre-tensioning happening on site, not to say that it doesn't happen, but typically it's going to happen in a factory on casting beds. So you have these really strong structures that are able to take massive forces inside them that the jacks mount off of, stretch the steel tendons, pour the concrete in there, relax the tendons, and apply the force through the entire concrete. What I'll do now, there's actually a video that I've put on to Learn. We'll get that, shrink that one, no, okay, I'll do,
Right click on Chrome.
okay, right click on Chrome.
You should just be able to new window.
Okay. Yeah, I'll get Learn happening again. I was hoping to find. Yeah.
No.
Oh, actually, no. That's okay. It's on Learn, but
It's just
we can find it on YouTube as well. So. So I think fairly good video presentation on pre-stressed concrete. It's for bridge beams, but basically the technologies or the concept's the same. Yeah, I think so.
Now here's our typical stop end that would be used to orient the pre-stressing strand that we would use to apply that compressive force to the beam end. Now note, these strands are not tensioned, they're slack. So there's no danger here. You must be very, very careful with fully tensioned pre-stressing strands, because there's a massive amount of force that can be contained in each of these strands. This particular strand, in fact, we would actually tension up to a load of 209 kilonewtons, just one strand. So what we would do, these strands would be jacked up, they would be pulled back, they would be essentially stretched, they would be put into that very large amount of tension, 209 kilonewtons of these.
So
the concrete would be passed around the strands into the appropriate cross-section. Once that concrete has reached the specified strength, specified compressive strength, then the strand will be gradually released, thereby transferring that force that was in the strands when they were stretched into the concrete. So that very large force of the strand will be then applied as compression into the beam itself. Now, notice that this strand layout is a far larger number of strands closer to the bottom of the beam. The bottom of the beam, the top of the beam would be just 50 mil underneath the actual bottom of the strand, 50 or 60 mil. The reason for that is, not only do we want to apply compression to the beam, We also want to apply a bending moment to the beam as a result of the pre-stressing operation. So because that overall position of the strands is eccentric, it's removed from the centroid of the beam, that enables that application of pre-stress to also apply a bending moment that will counteract or act against and relieve the bending moment that results from the applied loads, the loads that we apply to the beam under working conditions. Let's step back over to the finished beam itself and go to the final steps of the final aspects of how a pre-stress bridge beam works.
Just quickly, so to put it in a little bit of context, he was talking about putting a force of 209 kilonewtons on each strand. So typically, if you're designing wind bracing for a house, or so you'd be looking at about 15 kilonewtons of force on the side of a house. So we're what's that? Like a factor of 20.
A order of magnitudes higher.
Yes.
So this beam is one of our finished products. This was actually cast not long ago on this bed itself. Now, you'll notice there's a bit of a gap between the top of the beam and the actual bed itself. This is a result of what we just spoke about. When we apply that compressive force from the pre-stressing tendons, pre-stressing strands, not only do they apply that beneficial compressive force to the beam, but they also apply a moment that relieves the moment applied to working conditions. So this moment that's applied by the pre-stressing operation results in the beams actually cambering up. The beam will actually lift up several millimeters, 10 millimeters, whatever the case may be, depending upon the beam and the pre-stressing amount layout used. It will actually camber up. Now this is beneficial with regard to the deflection checks as well too. Generally for bridge beam design, we don't need to carry out rigorous deflection checks. But from an aesthetic point of view, you don't want to be visually sagging on site. So this natural camber that results from the pre-stressing operation itself will help eliminate the potential that that beam would be visibly sagging on site as well too. Finally, you'll notice as well too, we've got shear links in the beam as well. The shear links we use in the bridge beam would really be not substantially different from what you may be accustomed to for reinforced concrete bridge beam design too. So again, so bridge beams, pre-stressed concrete bridge beams would also make provision for shear design, shear reinforcement. So in order to summarize how pre-stressed, precast bridge beams work, beams are intended to carry flexure as well as shear, but that flexure that they're going to carry results in tension in one face of the beam. Concrete is not good in tension. In reinforced concrete, you use bars, steel bars, but in pre-stressed concrete design, we apply compression in order to overcome that tensile stress in the beam to the flexure. The force is applied using pre-stressing strands. Pre-stressing strands are stretched. Concrete is passed around the strands in pre-tension concrete, and the strands are slowly released, thereby applying that pressure force to the beam, while simultaneously applying a moment to the beam that also acts to relieve the applied moment. I should also point out as well, too, that what I've been speaking about here relates to pre-tension, pre-cap, pre-stress bridge beam design. There is also post-tensioning, post-tension bridge beams, which are slightly different, or rather different from pre-tension bridge beam design.
So effectively what you're doing is you're creating tension at the top of the slab so that when it actually sort of like gets the weight, it actually goes into, you've created tension at the point that it's least going to be affected, so that then it gets pressured down and it sort of like goes into a neutral state rather than, because there's obviously if it's gonna do that, then there's tension here, but that's not the point of the slab that you want to be most concerned about. You want to be concerned about what happens down here.
Yeah. notice with their bridge beam, which is not too dissimilar to what you do on a slab, or say a concrete element which you want to span from one point to another point. The majority of their strands were located at the bottom of the concrete bridge beam in that case. So that's because at the base area, that's where it's got the greatest tensile forces. At the top, it's coming into compression slightly, because as you apply a load to it, it wants to deflect downwards, it's stretching at the bottom. If you get your steel tendons, and you stretch them like that, and then release them with the concrete, it actually bends the concrete up slightly. So it produces a camber on that concrete element that when you apply a load onto it, it actually settles flat. So it's about calculating the amount of force that has to be put into that concrete to lift it up to counteract the weight that will be applied to the top of it. So talking about bridge beams, talking about very large loads being imposed on those.
On a very wide span.
Yeah. But yeah, it's the concept is no different for a slab which is spanning from one point to another point. If you want to keep that slab quite thin, if you were to just use standard reinforcing, well then you'd get deflection of that slab, but also you probably wouldn't be able to do large spans. You just wouldn't have the strength in that. But also, if you start stretching steel a little bit, steel will actually stretch a bit until the point where it doesn't want to stretch anymore, and then you can keep applying load and it will snap. But if you bring it out to a certain point, well then that the counteracting the tensile force happens almost immediately when the load is applied, rather than allowing the steel to expand that little bit once it starts deflecting, if that makes any sense. Probably, actually, I don't have I didn't put a video on Learn about post-tensioning. I noticed that one is up there. Maybe there was quite a good video on post-tensioning.
Let's have a look at the very good video.
What's that?
Let's have a look at very good video.
Yeah, I think this is actually one. Yeah, so it doesn't actually have any commentary on it, but what it does is it shows what's happening step by step, and we can chat about that as it goes through. So just working out the length of all the cables, so to measure them up and roll them out, roll them up to pack them away. Nurling the ends of them, so you can pull them through, and that stops them just getting pulled all the way through. So that's marking on the formwork for the placement of the I don't know what they're called. These accommodations where the pollets go attentioning the steel. It'll be like a form of a rebate. Yeah. So this thing here that they're casting into place there. So that will end up being inside the slab, and this is the conduit that the post-tension cables go in.
So that is actually permanent conduit that it's in.
Yes, yeah. So that conduit sits inside the slab, and the steel tendons go in there. Then you cast the slab. Once the slab has gone off and hardened, then you stretch the tendons.
Ah, right.
So that's why it's post tension.
So there's absolutely no contact between the concrete and the tensioning, which is
spot on.
Yes.
Yeah, whereas with the pre-tension side, contact is absolutely everywhere too.
Yeah. the drawbacks of the post-tensioning is that you can't be as accurate with the forces that are applied into your slab because you've got this conduit that's doing a little bit of this. Once you stretch things out, it applies some forces eccentric. Whereas with pre-tension concrete, you're doing that in a factory, everything can be exact and you can get those forces exact. But the benefit of this is it can be done on site.
So it's somewhat labour intensive though.
Yeah.
Well, the other one would be labour intensive, but not nearly as, because it wouldn't be actually guys putting it all together on site. It would probably be.
And you got like 5 people here going along with twist ties,
Yeah,
essentially.
Yeah.
You
Yeah, there are now battery powered tools that you can use for tying off steel as well. But yeah, I know a steel fixer who he still reckons he's much faster doing it by hand than the machine. So
right.
yeah, so you get pretty quick at it. So that's the steel cables coming out. That piece that was cast in there early on against our formwork, and then they've put the little I don't know what that's called, but then little collets go into there, and they enable the cables to come one direction, but then block them off from springing back in. So that's just a way of marking them to measure. So you can say, okay, they're all. This is the length they are today, or at this moment in time. And that's a hydraulic jack, just stretches the cables.
Oh, that's just to make sure. It's actually pretty rough technique if you're just using a tape measure.
Yeah, they've got a gauge for what tension is going on there as well.
Yeah.
Yes, but I don't think you've got to get nearly the same sort of accuracy that you get within a factory controlled
No.
pre-tensioning scenario. But see those little bits, so they've just filled that with concrete, you'll see those around this building here. And now what they're doing is they're mixing up grout to get pumped into the conduit. Tube on the other end, so they send it in one way, fills up the conduit, and then spurts out the other end. So when it spurts out the other end, they know that the conduit is completely filled. And you also see remnants of these grout tubes around the place in the concrete floors here as well.
They build very, very good structures and stuff.
Yes.
Yeah.
Yeah.
So in terms of pre-tension concrete, that would really only be necessary for something like bridges.
Yeah, or where so with your research task 3, I'm getting you to I'll just get that stopped. And then you're using it for scenarios whereby you can crane elements into place.
Right.
It's probably just behind there. Oh, here we go. So, pre-stressed concrete elements, that's something that has to happen in the factory. You don't want to build in the factory, obviously, you want to build somewhere else, so it's all about transport. So you think about, using it when you transport things to site. Whereas with that building they were doing with the post-tension, massive building, doing large floors, it's not feasible to be craning elements into site, and the bulk of their structure was concrete. Whereas for the research task 3, I'm getting into look at doing a steel portal frame and then bringing concrete elements into that. So that's a scenario where we can be craning bits and pieces in. Okay, we can probably scoot through that fairly quickly. So here we go. Got pre-tension concrete. So some systems are hollow core where the floor slab is not completely solid. This reduces the volume of concrete required and the overall weight on the building. So yeah, you still get the benefits of those concrete floors in terms of fire resistance and reduced noise transmission, but you're using less concrete for achieving that. Also enables the running of services through here without compromising your fire resistance as well. Whenever we've got, if we have a sole occupancy unit underneath us and then one here like this, the floor has to have a fire resistance level to stop the passage of fire if a fire was to happen down below us. As soon as we go putting PVC pipes and things like that through, well, the fire resistance level is compromised straight away. So that's a way that fire can travel between floors. One way of stopping that from happening is you put a fire collar around your PVC pipe, but when it heats up, it just closes up, crimps the PVC pipe and doesn't allow passage of fire. So that's one way of doing it. Or another way is if you're using hollow core slabs like that, you core down into this top bit here and then you run services through there. It all depends on the size of services and things that you're running. You probably wouldn't be able to run a main sewer 100mm pipe through there for any great distance to be able to get your faults, but you may be able to run one for a short distance. Also, the pre-stressed concrete, pre-stressed strands are located in these positions here, so you can actually core down into those hollow cores without hitting any of those pre-stressed strands. Other systems involve profile or T-beam shapes where it's basically a slab and beam type scenario that can incorporate pre-stressed elements once again, or pre-stressed tendons in there. So yeah, you can cast in thinner sections, reducing overall height of building. So sometimes that's important. If you're doing 30 stories or so, another 100mm for every story, that adds up to one more floor. So one more floor might be another 200 square meters of net lettable area within the city. It has value. Enables a lighter structure, larger spans, watertight slabs. So any concrete slab can be watertight. It's not unique to precast. Faster construction because everything can happen off-site and then be brought in. So without that post-tensioned concrete, that large building they were doing, that would have to happen in stages, and it's a fairly slow process. Less deflection, or deflection can actually be counteracted, so you can put a camber into something, and then greater crack control as well.
Well, it's interesting because when that during that open day with that day that they had presentations, and he was saying $50,000 a week for site costs. Now, if you've got lads doing that post-stress stuff for 3 months, because you've shipped this in and done it within sort of like a month, you've just gone and saved $50,000 a week, 2 months.
Yes. Yeah, so $200,000.
$400,000 a lot, yeah.
Yeah.
So that's a big saving.
Yeah.
But then you've also got the new cost now of 100,000 for the crane.
Plus the crane, yeah.
Yes,
that's right.
yes, it's about balancing all of those.
100,000 for the crane and also whatever
100,000 for the crane for the month,
Yeah.
as opposed to 50,000 in site fees for the extra 2 months.
No. 400,000 in site fees, right? So you start with 50,000 a week, 400,000 for 2 months, and then you work back from the crane, the premium on the pre-stressed blocks, and so that's probably going to be double whatever it is, whatever. So then you've got to work back your savings from there.
Yeah, and that's it. It's all like cost here or cost there, which way is going to be most cost effective, and which way is actually going to produce a good building as well. So, like, I guess you know about the Opal Tower in Sydney. That's been plagued with issues. No.
There's
a few.
That's just because like engineering standards, and I actually think that I think that there was water courses over there that they haven't taken account of.
Yeah. But there was also just poor workmanship that happened on site that wasn't fully checked as well, and the more you can avoid that, the better as well. Post-tension concrete, the stress and forces applied to the high tensile steel tendons after the casting and curing of the concrete. Steel tendons are prevented from bonding to the concrete by passing through a sheath that is cast into the concrete. So they are applying load to that, but from those stop ends that are cast permanently into the concrete, and that load isn't spread uniformly throughout.
I was just thinking
the slab.
the pressure from that end form is going to be, there's going to be an effect in terms of probably more load at that point, and then you do have your sort of like your zero moment in the centre, because you've got the pressure coming from both sides, and that's going to be the point of the greatest pressure.
Not sure.
It's just localised. It's a localised pressure at a single point.
But it is through a single element, so that pressure would
be distributed.
Be distributed.
Going through similar with that, with the post tension to concrete. An analogy that I've been thinking of for that seems like trying to carry a stack of books sideways.
You've got to keep the tension up.
It's like a stack of books. It's got absolutely no tension in it. If you were to hold it sideways.
No tensile force. Also
Zero
no
tensile force.
No resistance to tensile force.
But it fairly good in compression. But you want to carry the thing through, for some reason, just doing it stupidly, and you carry it sideways. You got to squeeze on the thing pretty hard to be able to keep everything from falling.
Yeah, exactly, and that's exactly what that post-tension concrete is doing.
Whereas pre-tensioned, it's more like you've got like 50 hands, and you're just holding each individual book.
We drilled a hole through there.
A bit of string.
All right. Can't go too wild with our analogies. One of the main differences between the two in terms of safety, though, is for work that's carried out afterwards. If, let's say, I'm a plumber and we've decided to put an ensuite into this classroom, and we go cutting a hole in the floor for running a drain or something like that. If it was pre-tensioned concrete and I hit a strand, well then it's probably not going to have major adverse effects on that slab. Well, not nearly as bad as if it was post-tension concrete. If it was post-tension concrete and I hit a strand, that strand springs back, and it may destroy the slab in the process, or may hurt people, or cause all sorts of damage. So, post-tension is a little bit more dangerous in that retrofitting type scenarios.
Pre-tension is more dangerous.
No, post-tension is more dangerous.
I was told
Because-
the pre-tension was more dangerous because it's with the pre-tensioned ones, the concrete will explode, but the post-tensioned ones are less dangerous because basically it's got the channel that runs back and separate. I don't know.
Yeah, no, I've always thought
You've
I've
always
always thought the opposite, because the post-tension doesn't actually bind well with the concrete.
right.
And because it's not actually bound to the concrete, and the forces are applied at either end of that concrete slab, that when it is cut, it can
It'll
spring back. Whereas when something is cast into the concrete and has continual
See, I
bonding
could have got it
with that,
completely wrong, but
yeah.
you and Stephen need to have a conversation.
maybe we'll have a chat with Stephen about
I
that.
think the main thing would be pre-tension versus post-tension. The post-tensioned, because it's not binding to anything, it has to have a stronger tension in the actual cable whenever it's in use. But the pre-tensioned, because of the fact it's binding across the entirety of it ends up having less tension in the cable
See, I thought
for a similar span.
I thought it was the opposite, but how about you come back to us next week?
Yeah.
Have a conversation.
I see Steve in the live stream. Yeah. But one of the great things about post-tension is it can be used in a retrospective fashion as well. So very famous buildings. Anybody know that building? Well, I'm giving it away there.
Where's
No,
Falling Water?
Falling Water. Actually, I don't know. Actually, that's a really good. I don't know where it is.
Because I initially read it as Waterfall, and it's
Yeah.
like in New South Wales, but no.
No, it's in the States, but I don't know the States very well.
No,
The
I
States, I don't, yeah. Anyhow, so Frank Lloyd Wright, famous architect, one of his very famous buildings, but as with some experimental architecture, it sort of needed a bit of help later in life. So so they've threaded cables through sections and post-tensioned them to help carry the cantilevers. So with our cast in situ concrete, we have to produce formwork. Some of that can be temporary formwork in terms of timber formwork with acro props and H frames to stabilise the whole lot, and then that can get all stripped out and used again in other buildings. Otherwise, we have permanent formwork like Bondec, like we saw, like we've seen previously. So that stays as part of the slab.
And it doesn't actually, does it have mesh in it? It does have mesh.
It still has mesh in it. It still has reinforcing bars introduced into it. It doesn't form the entirety of the steel reinforcing. It provides some steel reinforcement, and at that plane where it's most needed. So it's very efficient in that regard.
Also saves you 40% on your formwork.
Well, that's It's very, very quick and easy to lay, and it requires less propping than your standard formwork. So this is the formwork that's going to be taken away. You can see the extent of the work that goes into setting up all of that propping. And and when you require more propping, you've got more opportunity for something to fail as well. Not to say that Bondec or Lost Form doesn't fail as well. So people can get a bit complacent with that as well. There have been failures as a result. Other forms of formwork is slip forming. So that's where you're casting something and then you just keep bringing the formwork up. So typically used for lift shafts and things like that. Oh, that one wasn't slip formed. That was. You can see the sheet joins in that lift shaft there.
That would be similar to like a kangaroo crane.
It's a kangaroo crane.
Crane that builds the building it's on.
Right. Yes.
And then it jacks itself up to the next floor and continues building.
Yeah. Yeah. Exactly. So that's what this slip form is doing. So it's casting that element that it keeps climbing, essentially.
So does it need to cure for 3 days before the next layer it's for you?
I'd imagine so. I don't know.
Right.
Yeah, I'd probably want to be queuing for a little bit longer than that. But I guess it all depends on, you know, the amount of surface that you're bearing to, and what the depth of your lifts are for your concrete placement as well. So as we saw in that pre-tensioning video, concrete it's not malleable, but it can be bent. So we saw that bridge beam bend up under those forces. It also shortens. So as we apply more and more and more load, buildings do get shorter. Now we're talking about very small increments, but they do get shorter. So on the bottom floor of a building, you experience your most shortening because let's say we've got another 24 stories above that. So our window accommodations, things like that, they'll end up being slightly smaller than when they were cast, and that needs to be accounted for. Not by, you know, certainly not by the drafters in the office or them, and possibly not even by the architects, but by the engineers to work that out. Also, concrete can be used for cladding panels. So not just as structural elements, but as elements that get included onto the outside of the building. So that's is that Festival Theatre, I think. That one there, and that's the Sam Stagg building on North Terrace, which I think is it's quite a beautiful structure, nice use of concrete panels. So yeah, concrete panels can be quite interesting, or can also be a bit naff in some situations. No, shall I leave? I'll stop recording that. So any questions in regards to that concrete? It's all making plenty of sense? Yeah. Yeah, we did actually. There was a student studying this subject who was in the day class right at the start, but he ended up being too busy and he couldn't keep the class up. He actually does post-tension concrete, so it would be good to have him along. But so that's that pre-stressed concrete video. Yeah, some more slides on, just pictures and so on about post-tensioning. Concrete testing, so particularly for important structures and large projects, the concrete suppliers will want to take samples and cure them correctly, because if there's any faults that happen later on or any litigation that happens as a result, they can go, well, here's our sample from that batch that was correctly fibrated and cured. We do the compression test on it, etc. It's not the problem with the concrete, it's the problem with the application also. So, but also it enables continual, quality control for concrete and testing of aggregates and so on, and testing of ideas. Yeah, concrete can actually be, it can actually get incredibly complex with all the different admixtures and agents that enable high slump concrete, so or for fast early strength concrete, or
massively increased strength.
Yeah. So there's all sorts of things you can be doing with concrete to achieve different results. Typically in the summertime, your concrete will have retarders in it to stop it going off quickly. If you're pouring in the winter time, well, then it will have accelerators in it to get it to give it high early strength. Some information here about formwork and also about concrete bolts, which is C. So we can see 717. Let's have a quick look at some formwork. Does anybody know that building?
Not
Yeah, Great Ocean Road down near, what is it, Apollo Bay?
no.
Yeah. Yeah, I don't know who owns it. Pretty. Yeah. So just off the screen where my cursor is there, that's the ocean. So it's a pretty spectacular position.
Reminds me of that Hitchcock film.
One.
I can't remember which one it is, but
It's not too many.
Yeah. So all this is as a result of formwork. So whenever you see concrete formed into a shape, it's as a result of formwork. So here, this is form ply. So it's a 16 mil thick sheet of plywood that's very strong, and it has a film on the top of it to give it a really smooth finish, which that then applies to the concrete.
so with form ply, 16 millimetre, very strong. It's a form of structural ply, is it?
I don't know what people typically don't use it in a structural sense, in a permanent structure for bracing or anything. It is incredibly strong ply.
Right.
Yeah, it does counter a lot of deflection.
Yeah, because
So,
I mean, like you're
yeah.
describing to me a material that could be used for alternative purposes, aren't you?
Well, yeah, it does get. Yeah, you see, it's a bit of a aesthetic movement, architectural movement to use it for furniture and things like that. See it used about a place for developed for use as formwork, of course. But yeah, you do see it used for all sorts of things.
I mean, the thing does hold up liquid concrete
Yeah, 100 mil.
in quite large spans, so it has to be fairly strong.
Yes, it's quite strong. But yeah, I've seen furniture made from it. So, it's not cheap though.
Right.
It's expensive.
It's expensive stuff.
Yeah. Well, yeah, more expensive than your standard
Your average
ply.
ply.
Yeah. So that's casting inside a casting factory, and so benefits of doing it in there. Okay, controlled environment. You've got everything at hand. You've got gantry cranes for picking things up and so on, moving things around. And also, concrete can be used efficiently as well. We know about that. Here, that's. I think that was that might have been at the old TAFE at Marston. So forms set up with scaffolding. So that's the Acro forms, same company as your Acro props. Forming up a stormwater pit. So you've got your rigid steel forms on the inside, and then form ply to carry that above the ground. So with your concrete slab on ground, obviously your formwork for your concrete slab is the dirt. So yeah, you can use all sorts of things for your formwork, and whatever form the formwork takes is the form of the concrete will take. This is a way of holding your forms together. So with Z bars, and then locking nuts, and then on the inside you have those spaces to provide the sheath, and they end up getting lost to the concrete when the Z bar gets pulled out.
So the question is then, is that a way that water ingress?
No, because your concrete will cast around that.
Oh, your concrete casts around that, and then there's no real breach there. It's all bound.
Yeah,
Okay.
yeah. But you'll end up having holes then through that slab.
Right.
And some simple formwork made up for casting barbecue tops. Yeah, concrete's moved around in kibbles, although so that's more for lifting concrete into high-rise situations. However, the technology around concrete pumps has pretty much replaced that. So now you can
You don't have to have a sled.
yes, you can be pumping concrete up yeah, hundreds of meters in height. Well, actually, I'm not sure how high what head pressure a piston pump will do, but yeah, they'll come up to quite a height. Yeah, a couple of different types of concrete pumps. There's a piston pipe, and then there's this rotary one that basically squeezes the tube and pushes it up. But the piston pump is much stronger, but really noisy.
Right.
It's basically a giant car engine.
Yes, yeah, and it's just goes like sucks concrete in, pushes it, sucks it in, pushes it.
Right.
Okay,
Oh,
and
wow.
there's a list. There's a link there to the Delta Core slabs as well. So also, yeah, recording. Yeah, great. So another common material in commercial construction is steel in several different forms. So we've got heavy duty hot rolled steel sections, and also lightweight rondo style steel for all of your infield works. So once again, I guess, yeah, lots of design freedom with steel. I guess the design freedom extends probably as far as your budget allows. So steel sections come in different shapes and sizes. They are either hot rolled or cold rolled. Sections are often referred to by abbreviations. It's important to memorise the short name. The following slides feature the commonly used steel sections. So your I-shaped sections, you've got either UBs or UCs. So they're universal in terms of that shape gets used everywhere. And let's say if UB 315 is going to be the same here as it is in another country. So with our beams, like this one here, they're rectangular if you draw around the outside of them, they're rectangular, whereas UC is square. Could anybody think what a TFB would be?
Triangular.
Good guess.
FB, F.
Yeah.
Something B.
Yeah. So what would F stand for in a beam? Does anybody know? We've got. Well, I'll let you know. So with our beams, we've got webs and we've got flanges.
Flange, right? Flange,
Yeah.
triangular flange beam.
Yeah.
What does it look like?
It looks a lot like this, but it's a tapered flange
Oh,
beam.
right,
So it's exactly.
So literally sort of like there's your beam, but then that just flanges in.
Yes, yeah. So the flanges taper, and that allows you to be lifting things in.
You're
like
giving
this.
yourself additional strength.
Yeah.
Breaking up your line.
Yeah.
So more like two wires on top of each other.
Yes, yeah. Yep. So your names of your beams give you information about that. So for 310 UB, the depth of that is 310 millimeters. And then typically you've got, if we were to go to One Steel catalogue, also it would give you all of this information. So the thickness of the web, the thickness of the flange, the depth of the web, etc., and the radius or the breadth of the flange. It's also a good thing as drafters to secure either rubber panels or CAD blocks of all your steel sections. So you can just drop them all in. Also commonly known as a C channel is the parallel flange channel. So that's where you've got your flanges. Move around a bit. Your flanges parallel to each other. So when you cut it in a cross section, it makes the letter C. Utilising flat side is required against walls or the edges of canopies, so it makes a good pitching beam for, let's say, a concrete slab to go in, or for some bond bank reinforcement to go in and then casting into. Also used for the end of retaining walls, so your retaining walls for concrete sleepers, you'll use I-beams throughout and then a parallel flange channel at the end. We've got a couple of different types of angles. So the first one we've got here is the unequal angle. That's where one side is longer than the other. So that's designed for typically for spanning a distance. So it's got depth of a member. Or there's equal angle. So can also be used for some sort of pitching plate or so on walls. Also for when you're doing tilt-up concrete slab or precast concrete walling in situations where the corner join is not important, you can actually use these for locating the base of your concrete panels on your concrete slab, but also quite often used up the other way for to tie the concrete panels together at the top and provide a fixing point for trusses to go onto. Then you've got your various different hollow sections of steel. So that's a square hollow section, so an SHS for a square hollow section. Can anybody think what a CHS would be? I think I spoke about that the other day. Yeah, circular hollow section. Otherwise known as a pipe. Then we've got our rectangular hollow sections. So, like your universal beams, universal columns, you've got to be using square hollow sections for when your forces are going to be roughly equal in the same direction. But when you're spanning from one point to another, well then a rectangular hollow section is going to be more important.
6 by that long.
Yeah. Or I just used rectangular hollow section recently for screen, like having the deeper section facing where the forces from the wind are going to be on the screen, because you know you're not going to get strong forces sideways, you're going to get strong forces. Yeah. So wherever you're going to have forces predominantly coming from one direction. Your steelwork is typically joined together with steel cleats. Now those steel cleats, they may be to join, let's say, Z purlins on top of a portal frame, or it may be to join portal frame members together. And you also have plates welded onto the stanchions of your portal frame as well for fixing. Now this is a very common fixing detail whereby you have threaded rod cast into a concrete slab or a concrete column, some concrete member, and then you have nuts threaded onto those rods. Drop your portal frames on, and then you thread nuts on the top of that and tighten them together. It enables you to get the height of that portal frame exact. So we've got, so it's not just steel portals, you also have various different trusses, etc., made from hot rolled steel members. So this is a wall truss. You do something like this for when you're creating a parapet or an end wall. So you can't see any out this window, but if we would walk into that main assembly area and then look toward where that Danpalon siding is, we've got wall trusses along the ends of this building there, creating an end to that sawtooth roof. So our I think we talked about purlins and girts in portal frames a while back, didn't we? Does everybody know? No?
I don't remember.
Yeah,
I know
okay,
we talked about it.
Yeah. So purlins are your members that go on top of your roof that span between your portal frames to mount your sheeting on for your roof. So that's your purlins. But on the walls, they're known as girts. So all your horizontal members are called girts, and the members that will take gravitational loads, they're your purlins.
So they're buttons, but they're useful buttons.
Yeah. So yeah, they'll still take wind loads. They'll have to stay rigid under wind or resist deflection under wind and transfer all those forces to the size of portal frames. But here in this cross section here, with our wall truss, or our parapet section, we've got girts in between our various different vertical members. And what do we have? No, we don't have a leader to that. So here, well, that vertical member is the end of the truss, and then we've got cleats welded to that truss, which mount our girts. And that truss has also got a cleat on here that's carrying that universal beam for another section of roof. So possibly that's a sawtooth roof situation, probably a bit, or not the same as this. This sawtooth roof situation is made up of trusses, and they're bound together, and then we've got girts on the ends of those trusses. Whereas this situation here, we've got wall trusses spanning from one point to another, and then sawtooth coming off of that. So this is a typical way of drawing up your connection details. You draw your cleat in here, and then you draw your fixings as X's. For doing this in detail, you may also draw in your welding and specify your welding as, like continuous fillet weld or a butt weld. So butt weld is when you've got two members butting up to each other, and then you weld, and you melt the joint in between those. And a fillet weld is when you've got them running perpendicular to each other, and you do a fillet.
It's exceedingly easy to do.
Yes, yeah, fillet welds, yeah. It is, but
welds are a pain in the butt.
that's one way to remember it. Yeah. So some of that welding can happen on site, but it's much better to get your welding happening in a factory, prefabricated, and then brought out to site. The issue with that is you have to be far more exacting with where everything goes, which means you have to be exacting with your drawings. So that's one very important aspect of the drafting process, is it enables you to work everything out to a really detailed fashion before anything goes out. So it enables that prefabrication. So one very good practice with your drafting is always draw things to scale whenever you can. So all the time, basically. So you get these details, and you do everything to scale so that you know that this is exactly 638 millimeters from this point also.
Yeah.
And that can be detailed up and exactly so that when that gets welded onto there in the factory and it goes out to site, the bolt holes line up. Also, what we can see in this detail is we've got a box cutter here. Now this is not a common detail where this universal beam has been cut to accommodate that box cutter. That's definitely not a common detail. The reason that's not a common detail is because all of a sudden it renders that universal beam to be having far less strength than it
renders it compromised.
Yes, renders it compromised. That's a very good way of putting it. Thank you.
To pretty much whatever that distance there is.
And they may have re-welded a flange on top of that to increase the strength of that. But that's really not a common detail. What you will typically do is you'll have cleats on top of this universal beam standing up, and then some purlins attached to that, and your roof sheeting up here to allow your box cutter to be hung above your universal beam without compromising the strength of that.
Like, why waste money in universal beam?
Yeah, yeah. So that's hot rolled steel. So we also use cold rolled steel for lighter gauge stuff. So top hat sections and furring channels. So top hat.
No, it's very general. It's a top hat section.
So top hat section is really very similar to a furring channel. I'll draw both of them up here.
Well, the simplest way to describe it is a cut section of it looks like a top hat.
Yeah. So top hat, like that, basically, and these are your fixing points here. Furring channel, pretty similar, except it's got angled sides, and you're still fixing in through these points here. Move a bit clearer for fixing. So top hat, that's because these sides are perpendicular to where the forces. Let's say we've got force coming this way. It resists that force much better than your furring channel. So your furring,
Tension.
So your furring channel, much easier for fixing. You've got so much more space for your tech drive or whatever to get in there and fix to. So that's typically used for battening out. If we wanted to put another plasterboard wall on the face of this wall, we'd fix furring channels on here, and then our plasterboard straight onto that. But top hats we might use for if we were doing that on the outside of a building and there's going to be wind loads happening on that.
Right, because the furring channels are actually very, very useful for acoustics.
Okay, more so than top hat.
Well, and I haven't seen references to them in terms of acoustic insulation. I've seen lots of references to furring channels.
Yeah, because typically a furring channel.
Furring channel, because of the fact that it resists less load, there's more flex in the actual material that you're putting on. So if you're putting a sound insulation thing in a sound booth or something like that, you would use a furring channel instead of a top hat, because top hat, suddenly you've now got a point on that wall which can now transfer sound out of the room.
Yes.
Whereas the furring channel, it's less likely to do so.
Yeah, I can see that. Yeah.
But I've actually seen it in terms of sound insulation. It's one of the things that massively reduces the sound acoustics in like all of that stuff that I've been doing for years. It's furring channels just keep coming up.
Yes, because they're typically used indoors as well. And what they do is they minimise the amount of contact from one material to another, and a lot of sound is transferred via contact.
Yeah. Well, I mean, it's interesting with the concrete because concrete's actually got very poor sound insulation. I mean, I kind of knew that sort of like because of something I used to do, some work I used to do, but when I was reading it was like, it's got really poor sound insulation, which is why you have problems with sort of like people hearing from apartment to apartment. Because I've experienced that hearing it from apartment to apartment, and I've also experienced the flanking noise involved in a multi-story construction, which is hell.
So many different ways in which sound travels. So it either travels through elements, or it finds holes in things, or it goes around.
It goes
around. So that's your top hats and your furring channels. We've also got Zs and Cs. So sometimes you use C sections for purlin, sometimes you use Zs. Has everybody here seen a Z or a C purlin before? So your Zs, as the name suggests, in cross section it looks like this. So that's your Z, and then you probably have your steel cleat here like this, fixed onto your universal beam, running down like that, and then you have your roof sheeting or whatever on top of your Z. Also Zs, make it incredibly easy for fixing. Once again, if you're fixing your Zs straight to something, well then it's easy to get your driver into there, not so easy to do with a C-shaped purlin. And Zs are really easy to join as well, because you get another Z purlin and you push it on like that. So they overlap, get the other one, put them on like that. Your Cs are like this. Oh, yeah, that's very badly drawn. Sorry about that. Straight up and down.
So that sucks, yeah.
Yeah, so that's your C purlin, that sort of shape. We've got a little bit of rays in there. And then that's onto your cleat, which is welded to your universal beam, and you bolt that on. If you were fixing that directly to your universal beam, not as easy to fix. So you can't get your driver straight in there. But then also they don't join nicely because you can't fit a C inside a C like you can fit a Z on a Z.
So what's the utilisation of Cs? Why specifically Cs?
Yeah, look, I don't know. I can't think of a situation. Look, you use Cs for your framing, like you can make portal frames from cold rolled sections and use Cs for that. So you definitely don't go using Cs for making portal frames. But you don't, I think Cs were the traditional way of doing things until somebody thought of a Z purlin, basically. And then, because pretty much everything you see going up uses Zs.
Oh, the only thing I can think of that a C has over a Z purlin is its better protection for the actual fixings, because less of it is exposed to direct waterfalls. And that's about the only reason that I can think of. Yeah, well, in here, well, hopefully you won't be designing any water getting in there anyhow. Some of the drawbacks of Cs, apart from fixing and lapping, is that they also they gather stuff in there. It's a fantastic home for birds and so on. We all like birds, but not in our purlins, so they do their nest in there like that. And also C purlins on your walls. Whichever way you mount them, they'll gather dirt and dust in there. Whereas you can mount
the
Cs.
You just have to make sure that it would actually have to carry a bit of strength in the joints, because the Cs somehow or another they just because there's that bending action that you can't get with the C. Because the C's got in place, you don't have so much steel to deliver the same strength. I suspect. Yeah.
Well, I think you have the same amount of steel in the C purlin or a Z purlin. Basically, it's the same profile, except one hooks the other way, and one doesn't. But this, that doesn't resist your forces to the same, your forces that are direct to the same extent that your C will resist those forces.
Because you're more likely to get shear force in your Z purlins.
And that's what I was thinking.
Yeah. That your Z purlin will also probably be slightly more expensive to actually manufacture, because that would probably have to be a 2-stage process.
Oh, no, I don't imagine.
A 2 or a 3-stage process, as opposed to a 1 or 2-stage process for the C.
No, I don't expect so. So your roll formers, you've got roll formers doing pretty tricky stuff. And your manufacturers of this, it's all pretty much plate steel goes in, purlins come out. I think because the manufacturer of these things is very automated.
I don't know what you call it in this, but it's actually the re-entrant corner issue with if you're doing the concrete slab. If you look at that, that's got 2 re-entrant corners, whereas the C, it's just there. You get pressure. Can I just get up?
Yeah, get up and draw.
Okay. You get pressure this way, right? Right. Pressure coming that way, right? You've got your weaker corner there, and that same pressure, which is coming that way, it's going to actually push you weak. This is a weaker corner as well. Whereas with the C, you've got pressure coming that way. And I don't know whether it's true. Yeah, but the thing is that was what I meant by the way steel. It's that sort of like, if you've got pressure coming that way, it's going to take that corner out, but it's not going to take that corner out.
Mm. So they behave slightly differently, and so
Yeah. I mean, it is only full roof, so.
So but as we know, the ability to fix things on site and lap things and so on, and save a lot of time on site can be is very worthwhile. So this picture, plenty of both hot rolled and cold rolled steel sections there. So all of our lighter blue stuff like this, it's all cold rolled sections. All of our red stuff with red oxide primer on it, that's hot rolled steel. So that doesn't have the protective coating of the zinc aluminum on it like the cold rolled stuff does. Can anybody say what they can see in that picture? Just reel off some stuff. What have we got?
I can see some top hats.
Yep. Good top hats here. University beam. Yeah.
What looks to be a square hollow section.
Yeah.
In fact,
I don't know, or it's going to be C section.
and in fact, these ones over here look like thinner square hollow sections, or they may not be.
Yeah. So we've got some SHSs here. This larger SHS there. We've got some smaller, some 50mm SHS coming up there.
You've got tensioning.
Yep. So brace. So that's some bracing rod through there, and then some cleats to hold that on as well. With your bracing like this, I think it's always important to have a detail whereby that can be tensioned up with nuts onto your cleats as well. I've seen a building done recently where they put the bracing in and it just sagged because it didn't have the capacity for being tensioned. Right. And so obviously that bracing is really doing nothing in that situation. It's doing nothing until the building has shifted substantially before it gets activated as well. So that's something that gets designed in. So here we go. Here's Zs, Zs and Cs. And some of your light gauge stuff, so your rondo channels. So that's for all your dividing walls and so on. So this one here, that would have light gauge steel channels in there, but also various different ceiling grid systems, etc., made up of light gauge steel. So portal frames made in a variety of shapes and sizes, usually from steel, but can also be made from concrete or timber. Did I tell you about the performance of a timber portal frame in fire that I saw once? I don't know if I mentioned that before. So there's a big oil recycling plant in Wingfield that caught a light many years ago. Right next to that, there's a whole heap of buildings that got absolutely baked, but right next to that was a timber portal frame warehouse that survived really well. It was amazing because a lot of your steel portal frames in that fire got all twisted and bent and everything. That timber portal frame warehouse, so it had the steel sheeting on the outside, so it didn't actually get direct flame contact. There was a lot of radiant heat going on, but I guess because of the spacing of that steel sheeting from the timber portals, that didn't combust. And it survived really well because because steel bends in heat. When it gets hot, it loses its strength and starts collapsing, whereas timber doesn't.
If you ever welding with steel, you have to weld both sides, otherwise you end up bending the steel onto the side of the weld.
Yeah. Portable structure is designed in such a way that it has no intermediate columns. As a result, large open areas can be easily created within the structure. So, used for all sorts of things. Hay sheds, warehouses, that sort of thing, where you want large, clear spans. So here you've got portal frame construction with very large, clear spans happening, but can also be used in residential architecture as well.
What is the structural difference between a portable frame and just like the standard Haynes 168 timber frame? What's the real?
Okay, so the real difference is in all the joints. That's basically the difference. So with a portal frame, you've got uprights and you've got horizontal or oblique members. That's it, same as your timber framing, except that the joints here at the knee and the apex stop that frame from being able to bend. So if we've just got a couple bits of timber and we nail them together and we have long pieces, we can easily bend that junction very simply. But if we've got some sort of flat plate joint, then it stops bending those sections. So all of the bracing ends up happening within the frame itself. And then any loads imposed from the top end up being braced against by all of your joints. So that's basically the difference. You can create a portal frame with some bits of timber and some bits of plywood. So triangle plywood gussets, screw them in, and you've made a timber portal frame.
So like theoretically, if you have a strong enough crane, you could just pick up a portal frame and move it somewhere else.
Oh yeah, yep. And that certainly happens. So often with your major big, like your really big portal frames, they come out to site as your rafters and your legs, etc. They come out all in separate pieces and they're bolted together, but they might be bolted together here and lifted up into place and put down. Several ways of putting them together. That also depends on how the joints are designed as well. Some portal frames are also erected whereby you put your uprights in first and you bolt those base plates down, and then you do your rafters upside down, have one bolt in from either end, and you rotate it around and then drop the rest of the bolts in as well. The design of all of your junctions is dictated by the forces that are going to be on there. Also dictated by the materials that you have at your disposal, but also by how you want those to be put together on site as well. So several different things you've got to think about for that. So advantages: speed and ease of erection. Building can be quickly closed in, made watertight, because you get this frame up in no time. Not the residential timber frames are slow either. Framework prefabricated in a workshop, and so it's not affected by weather. It's a lovely thing. Site work such as drainage, roads, etc., can be carried out until framework is ready. That is something that if I were to be a warehouse builder or so, I think that'd be it's an important point to get right, is getting all of your hard stand areas and all that compacted rubble down to create excellent surfaces for working in. Because I've worked alongside a lot of warehouses and hay sheds and all that sort of stuff going up, and you see guys in scissor lifts and whatever, trying to drive scissor lifts in the mud. It's just it's remarkable. Because you can't control the weather. Like, you get all sorts of weather. Sometimes you get really big dumps of rain, and so site works and so on is important to get right. It says no weather hold up during erecting the framework, but They're connected together in factories by welding, and site connections should be bolted. So you want to minimise.
So literally you're talking about
welding.
the only disadvantages of this steel framing system is literally the inherent fire, the inherent strength of the fire conditions.
Yeah. So if you get decent fire in there, well, in fact, you don't even need a decent fire. Before,
Just a
before
boring
yeah,
fire.
well, it's you can severely affect your structure, and then that's your structure gone, and it's not always so easy to isolate portions of structure for replacement.
Are you getting longer spans out of the material with that particular structure? Like with the portal frame structure, do you get longer spans out of the actual material, or is that a separate issue?
What you get is like your universal beam. I don't know this entirely. This is a very good question for an engineer. But with your universal beam, if we're going to span from point of support to point of support like that, let's say that's the span you get from your universal beam under a certain load. But with a portal frame, you can join those two together, and you're spanning from here to here. So rather than just from there to there, you're spanning from there to there, because they both push against each other. So it's that aspect of you've actually created just with that peaking structure. Yeah, but there's more to it than that.
Oh yeah.
And so talking very general.
And it's exceedingly simplified form.
It's exceedingly simplified form. Yeah. So some portal frame terminology there. So we've got bracing, and that typically happens in your end bays, because that's where your forces are greatest. Girts on the walls, purlins for the roof. So one way to remember that is our national anthem. It's the only other, but yeah.
Our land is girt by sea.
Yeah, exactly. Or our shed is girt by purlins. Same thing. Well, no, girt by Z's.
No, it can be girt by seas as well.
Yeah, certainly. Yeah, that's right. Yeah. So, some of your portal frame terminology. So, our columns and rafters. So very familiar name. Apex bracket and knee bracket or haunch. With those junctions there, if we've got wind coming from this direction here, my pen is wind coming in there, then that's going to get what's called a hogging moment, where it's pulling apart, whereas this one's got to get a bending moment where it's pulling together, and then this one's got to receive a bending moment in there as well. If we just have gravitational loads, well, that one's got to have hogging moment. Those two are going to resist bending moments.
So this is actually very similar to trusses in terms of like balancing out the bend of
No. Trusses, all the individual members in trusses help each other out. Well, these ones help each other out as well.
Yeah.
Right? So they're sharing. They're transferring forces from this one's taking force and it gives it to the others as well.
It's all very caring and sharing.
It's a similar process, but a different way of doing it.
Exactly. Yeah. So in your trusses, all your members get activated to help share that force. But what I was wanting to illustrate by saying that is that you then have to design those junctions to resist either those hogging or bending moments. So you've got to know whether your gravitational loads are the greater ones to be resisting, or your wind forces are the greater ones to be resisting. A few more, bit more portal frame terminology. So end frame, you've got mullions here for carrying your girts across that gable end. and also roller door mullions to help for finishing your C or the Z purlins, but then also for guiding and controlling the roller door. And then you'll have a strong beam, a header beam across that as well for mounting your roller door and for resisting the collapse of those two frames. So these frames are very well tied together through all their girts, but where you've got openings, you need additional support. And you see this one has bracing over those openings as well. Some more details. So in this detail here, we've got our universal beam there as our column or leg. We've got a gusset in here for strengthening that haunch or that knee joint. We've got a cleat here coming off to support our fascia purlin, which mounts a gutter to it. We've got our Z purlins mounting directly onto that universal beam. You'd probably only do that sort of thing if you're dealing with cold rolled sections. You can do it with hot rolled sections, but just the fixing is much harder into there, so you've got to do bolted fixings. That's about it. So yeah, so your base joints, as mentioned previously. So that's a very bad, bad occurrence. So you definitely want to avoid that. And you have to be really quite exacting with the locations of your casting rods, because they're casting, they can't be moved. You've got a little bit of free play, but not a great deal of free play with those.
You'd use a template though, wouldn't you? Some
but you've also got to get those in exact location in relation to the ones 12 metres that way as well.
Yeah,
and so your measurements have to be very exact,
very precise.
Very precise with those, because there's really no free play designed into any of this. And typically what you do is, so you thread nuts on, and then the portal frames go on top of those nuts, and then you thread nuts onto those, and then once that is all level and all in its place, it's all tight, those nuts get tightened up against each other, clamping into place, and then you put a non-shrink grout underneath. So you get that in there, so then your portal frame is actually transferring load onto the concrete, not just onto your fixing points. So there we've got some apex joints made by sections of cut universal beam, so it still has the flanges on it for additional strength. So it's important that this joint is strong, hence the use of wedge-shaped pieces called gussets, pieces to increase the strength and also increase the bolt area. Knee joints must be strong to support roof loads and prevent bending. Gusset pieces will be used to increase strength and give greater bolt area and prevent deflection under load. Also, you typically get small webs welded in here as well to help strengthen the flanges on those universal beams, because you have a concentration of forces happening in here. So portal frames need to be diagonally braced, and that can happen in all sorts of fashions. It can happen with rod with threaded ends, or it can happen using equal angles. You also have, do we have, I don't know that we've got any pictures of it here. No, we don't. Fly bracing as well. So fly bracing is where you've got let's say we've got a purlin coming across a portal frame like that. You'll have a diagonal brace coming from that purlin to the underside of the portal, and then back up to the purlin again, which means that any of the forces transferred onto that portal frame in a sideways fashion is going to be resisted by that fly bracing that happens there. Yeah, so girts are used for attaching external metal cladding. It can be fixed horizontally or vertically depending on the way the cladding panels are fixed, and also what's happening with your frames. Often, these structures like this are finished on the lower level with masonry to help with impact resistance and also fire resistance. That's it for our hot rolled steel sections. That one. So any questions on any of that?
I'm just fascinated by the spans that the portal frames can get.
Yeah.
I'm just looking at that and saying, why haven't they done that with timber? Which I'm sure they have in other countries, but it's not part of the old standards for Australia.
Yeah. Look, I don't actually.
It would be very interesting to see an
Yeah,
Australian
because-
standard for timber portal frame construction.
Yeah.
You know, I mean, that's what it comes down to. You'd have to get an engineer to sort of like, if you wanted to do it that way, you'd have to get an engineer to do it, something else.
Yeah, and then it's about so fixing with timber can be difficult, but then things like LVLs that resist splitting and so on end up making fixing of plates much simpler.
Yeah.
And you can use steel plates for all your joints.
That's right.
In combination with LVLs.
Yeah.
So I don't actually know whether I'd see more timber.
It'd be very interesting to see, but I mean, I think probably because you won't actually have to get your engineer to sort of like sign up on a lot of stuff, a lot of little stuff.
Yeah.
But you never know.
Yeah, and also, so your shed manufacturers. So you've got large scale shed manufacturers. They've got all their design software. It's all set up for doing this stuff with steel. They go, this is what we want. Boom, that's your design.
Which is why people go for it, because someone's got the resource to do it for you.
Exactly, and it's incredibly simple because all the engineering is done in a flash. Goes to council. Your shed is up incredibly quickly.
Yeah.
That's it.
But it's actually
that I think with the timber portal frames, there's a lot of, I don't really want to say backwards engineering, but more or less you're trying to rework a steel product with timber.
But you go to places like London and the markets in London, and they're all huge timber structures. I mean, they were all built in the 19th century. And, they're these massive flipping timber structures, and they are, sort of like, you do see a lot of steel, but, I have seen some in timber. And it's like...
The main reason why I think it's like, you start with the timber, and you realise, we can do a similar process with less material if we use it out of steel.
Yeah.
But then they realise, we're using steel, we can instead do this process instead, which is where the portal frame came in. And then people are realising, if we can do the portal frame with steel, why can't we do it with timber? Then they had to figure out how to do it with timber.
Yeah. I suppose it's just that what I'm saying